All right, so today we are looking at geometric series. Okay, so geometric series is the indicated sum of the terms in a geometric sequence. Okay, so just like an arithmetic series was the sum of all the terms in your sequence, that's what a geometric series is as well. Okay, so we're going to have a list of numbers that we're going to want to add together. Now, let's talk about this a little bit. So here's a pretty easy list where I'm just doubling the numbers every time. When we had an arithmetic sequence that we were trying to add together, right, to find our series, okay, we did kind of that Gauss trick, right, where we added these two numbers together first, and then we added these two numbers together, right? And with an arithmetic sequence, that worked out because the sums always ended up being the same. But you'll notice that's not the case here, right? These two would add to 34. These guys only add to 20. Okay, so I can't use that Gauss trick here of finding pairs and adding them together that way. So we're going to have to find an alternate trick that we can use. Okay, now we're going to build a formula to this. To be quite honest, I think with this one, knowing your formula is the easiest thing to do. Okay, but I do want to show you the proof of where this formula comes from because it's one, kind of neat, and two, I just think it's good to kind of expose you to some of these more advanced proofs. Okay, this will be a little bit more of a proof than you've probably done before in your math classes, but personally, I think it's pretty cool. Okay. Now, before we jump into that, a couple of things. One, there is a problem at the very bottom of this paper that is very different from all the other problems on this paper, okay? So don't tune me out before we get to that problem, okay? Two, we're going to run through this proof. I am not going to expect you to recreate this proof, but I want you to try to just follow along and see if you can understand what's going on. Again, I think it's pretty cool. I think it's kind of a neat little trick that we use sometime in mathematical proofs. This is not a proof like what you did in geometry. Those are very straightforward proofs. This one's kind of cool, okay? All right, so let's take a look at this proof of how we're going to find the formula for a geometric series, okay? So I'm going to start by just writing out my series. So S sub n, right? We use S sub n for the sum of the first n terms in our sequence, okay? And I'm just going to write out basically a generic list. So my first term is A1. My next term is A1 times whatever R is, right? My next term is A1 times R twice, right? Just like how in this example that we had before, right? This is 2 times our common ratio 2. This is this number times the common ratio twice. This is this number times the common ratio 3 times, right? So that's kind of what we're writing out here. So my next term is A1 times R to the third, right? And then A1 times R to the fourth, and then keep going until our last one that's going to be A1 times R to the n minus 1, right? And remember it's n minus 1 because in this guy, I've got 1, 2, 3, 4, 5 terms. So even though this is A sub 5, I've only multiplied 2, 1, 2, 3, 4 times. So even though it's the fifth term, I've only multiplied 4 times to get there. So that's why for A sub, our last term here, A sub n, you take A1 and you multiply it by n minus 1 times. Great. Okay, so that's just what this sequence is. It's just a generic way of writing out the sequence. So here's where we're going to do this trick. What our trick is going to be is I'm going to start by taking this entire equation and I'm going to multiply the entire thing by our common ratio R. Okay, so a giant distributive property on both sides of the equation that I'm multiplying by R. Okay, why am I doing that? Because I know that that's going to make this trick work. Okay, so I'm multiplying this whole thing by R. So on this side, I'm going to have R times S sub n. This guy, A sub 1 times R, I'm going to write as A1 times R. This guy, A sub 1 times R, when I multiply that by another R, that's going to be A sub 1 times R squared. When I multiply this guy by another R, that'll be A sub 1 times R cubed. If I multiply this guy by another R, that's going to be A sub 1 times R to the fourth, right? And so on and so on and so on until we get to the end here. And when I multiply this one by R, well, if I'm multiplying R to the n minus 1, and I'm multiplying it by another R. So R to the n minus 1 times R, R to the first. You add your exponents, right? So that's going to just work out to R to the n. So this last term is going to become A sub 1 times R to the n. Okay, so all I've done so far is I wrote out what this generic sequence is, and I took this whole thing and I multiplied the whole thing by R because I happen to know in advance that this is the trick that's going to work out for me. All right, now the next step in my trick, what I'm going to do is I'm actually going to subtract these two equations. Okay, so I'm going to take this equation and I'm going to subtract this from it. So I'm doing this one minus this one. Okay, you're like, well, why on earth are we doing this, Miss King? Because I know that this is how the trick works out. It's okay, just follow along. I don't expect you to recreate this. I just want you to see how it goes. Okay, so I'm subtracting these equations. So on this side, I'm going to get S sub n minus r times S sub n, right? That's what I have on this side of my equation. And then on this side, here's where the cool things are going to start happening. First, I'm going to have an a sub 1, okay? But look at what's going to happen. When I do this minus this, these two are going to cancel each other out, right? And when I do this minus that, that's going to cancel out. And then these guys will cancel out. And then these guys will cancel out. And all these dot, dot, dots, they're all going to cancel out. Okay, until we get to here. Right before this term, there's going to be one in here that's going to be a sub 1 times r to the n minus 1. That'll cancel with that guy. So the only thing that I'm going to have left, I'm going to have this a1 from the first one, and I'm going to have a minus this guy here, because remember, we're subtracting. So I'm going to have a minus a sub 1 times r to the n. And that's the only thing left, right? That's where this trick comes into play. I multiplied by r to raise all of these exponents by 1, so they'll cancel a whole bunch of stuff out. All right, cool. Now our goal here, remember, is we're trying to figure out a more concise way to write this sum. So I'm trying to rewrite what is S sub n in a nicer way than just adding it as a list of all these things. So I want to try to get this S sub n by itself. How am I going to do that? Well, I'm going to factor out an S sub n on this side, right? This has a GCF of S sub n. And when I pull that out, I'm going to be left with 1 minus r, right? Okay, and our goal, I want to rewrite this as S sub n equals something. So I'm going to divide both sides by the 1 minus r. So the sum of my sequence is going to be a sub 1 minus a sub 1 times r to the n over 1 minus r. And that is the formula that we're going to look at. Okay, now as a side note, you could also, on this guy, a lot of times people will factor out that a sub 1 there, because that's a common factor. So you could also write this as a sub 1 times 1 minus r to the n over 1 minus r. Or sometimes you'll see it as a sub 1 and then just times the whole fraction 1 minus r to the n over 1 minus r. Okay, so those three are all equivalent versions of the same thing. And just some people like one formula better than they like the other formula. That's all. All right, so that's our proof. And again, I'm not going to expect you to recreate this. I would just, if I were you, pick whichever one you like best and memorize that formula and then use that, okay? But it's kind of cool. And this is kind of more what higher ed math proofs are like, is they're using these cool tricks and thinking about something in a different and new and creative way, which I think makes them a lot more interesting than the geometry proofs that you probably did at some point where you had to prove that two lines were parallel. So that's how they go. All right, so back to our geometric series. Let's take a look at this. So this formula that we've just established is that S sub n is going to equal a sub 1 minus a sub 1 times r to the n over 1 minus r. That's our formula, okay? Or you can use a sub 1 times 1 minus r to the n over 1 minus r. Those, I think, are the two that I use the most often. Okay, but you could also use that third version if you want. Great, okay, so let's use this thing in action and see how this goes. It's not gonna be bad because we're basically just gonna plug into this lovely formula here. So to find the sum of the first 20 terms in this sequence. All right, so looking at this guy here, I already know a sub 1, that's 2. Okay, r sub n, right? That's gonna be the 20th term in my sequence. Okay, I don't know that yet and I need to know it. So that's problematic. So the first thing that I'm going to have to figure out is what exactly is that? Nope, I'm wrong. Okay, that was dumb. Let's think about that for a second. This is an r sub n. Why am I saying r sub n? That's clearly an exponent. It's r raised to the exponent, not r sub n. That was dumb. So I don't need to figure out what r sub n is. I just need r raised to the nth. So cool, we don't need to figure out any extra work. My bad. So using this formula, a sub 1 is 2, minus a sub 1 is still 2, times my common ratio r, I'm multiplying by 3 each time, that should be pretty obvious, raised to the n, we want the first 20 terms. Okay, and then it's over 1 minus r, which is still 3. All right, and then that is what we're going to throw into our calculators. Okay, so when you take a look at this, make sure you're following your order of operations. So I'm going to do 3 to the 20th, multiply that by 2, 2 minus that answer, and then I'm dividing. I know that's -2, so I'm dividing it by -2. So what a charmingly large number. So the sum of the first 20 numbers in this sequence is going to work out to 3,486,784,400. Lovely. All right, example number 2, this time without the oops. So taking a look at this one, right, I got to figure out what is my a sub 1 and what is my common ratio. So a sub 1 is pretty obviously 6, and then my common ratio, all right, if you take a look at these numbers, to go from 6 to -3, I'm dividing by -2, but I don't want to divide, right? I want to multiply. So that's the same as multiplying by -1/2. 3 times -1/2 is -3 halves. 3 halves times -1/2, that'll get you your -3/4, right? So we know that that's a good ratio. Cool. All right, and we want the sum of the first 8 terms. So we're finding s sub 8. And again, using that formula, I'm going to start with a sub 1, which is 6, minus a sub 1 again, which is still 6, times my common ratio, -1/2, raised to the nth power, which is 8 in this case. And I'm dividing it by 1 minus my common rate, which is common ratio, -1/2. Lovely. Back to my handy dandy calculator. So -0.5 raised to the 8th power times 6. 6 minus that number. And then divided by 1 minus -1/2 is going to be 1.5, right? 1.5. Which is that charming thing. Okay. And again, I want to make that into fraction form. So the sum of the first 8 terms in this series is going to be 257/64. Lovely. Okay, so we got that one. All right, now this next guy here. So this one looks a little bit different, okay, because it's written in summation notation. We talked about that before when we did arithmetic, but we haven't done it with geometric. Okay, so the first thing that we want to look at here is you're looking at this, and that doesn't look like your standard rule, right? Our standard rule, we usually have a initial term times a common ratio over and over and over again. So the first thing I want to do is I want to kind of look at this 3k, and I want to rewrite it so that it looks more like our normal form, okay? If I want to write 3 to the k power, that is the same thing as 3 times 3 to the k minus 1, right? This is, if I added my exponents here, I'd get k. So this is the same rule as this guy. It's just written a little bit differently. And then from there, I know that this is my starting term. So that's my a sub 1. And I know that this is my common ratio r. So I just have to be a little bit creative in rewriting it. They won't always look like this. It just happens to. And I want the sum of the first 6 terms of this sequence. I've got A1, I've got R. So the sum of the first six terms of the sequence, which I know because it tells me to go from the first term to the 6th term, okay, is going to be A sub 1, which is 3, minus A sub 1 again, which is still 3, times R, which is also 3, raised to the 6th power, because we're doing 6 terms, over 1 minus R, which is still 3. Okay, turn to my handy dandy calculator. 3 to the 6th times another 3, or 3 to the 7th, is the same thing. Subtract that from 3, divide it by -2, and the sum is going to be 1,092. And there we go. Okay. All right, now we come to this last problem. This is the one that I mentioned at the beginning. Do not skip out on this problem, okay? If you're looking at this and you're saying, oh, that looks like exactly the same thing, I can shut the video off now. No, don't shut the video off. This one's different. What makes it different? This guy right here. Notice that before we did from the first term to the sixth term. We're not doing that now. Now we're only doing from the third term to the ninth term. You can't just use this formula. This formula by default runs from the first to the sixth term. It's not as simple as just changing this to be whatever the third term is. It won't work that way, okay? So here's what we're gonna have to do. Here's an example of just a random other sequence, okay? So if I wanted to add all of these numbers together, I can do that pretty easily. 2 plus 4 plus 8 plus 16 plus 32, and figure out that my answer is 62, okay? So the sum of this sequence I know is 62, okay? Now here's what we're gonna do. This formula is asking us for the sum from the third to the ninth. I don't have that many terms, so I'm just gonna say, well, what if I just wanted the sum of these guys here, okay? I can't just plug this into this formula, but here's the trick that I can use. If I wanted to find just the sum of these three, okay, what I could do is I could say, well, I know the sum of these two is 6, and the sum of the whole thing is 62. So if I take the 62 and I subtract 6, that means that 56 has to be the sum of what's left over, right? And if I check that, 8 plus 16 plus 32, bam, there's my 56, okay? So that's exactly what we're gonna do here. This problem is asking us for the sum from the third term to the ninth term. So what we're doing is we've got a list of 9 terms, 1, 2, 3, 4, 5, 6, 7, 8, 9, and we only want this sum right here. So what I'm gonna do is I'm gonna find the total sum, so the total sum from the first to the ninth, and I'm gonna subtract from it this missing piece over here, which is the sum of the first to the second, okay? So I'm gonna do this sum minus this sum, and that'll give me what's left, okay? That's what we're doing in this problem. So in order to figure this guy out, what we're gonna have to do is I'm gonna figure out what is the sum of the first 9 terms, and I'm gonna subtract from that the sum of the first 2 terms, not the sum of the first 3 terms, right? Because I want the third one included in my sum, right? We want the third to the ninth to be included. So I just want the first and the second excluded. Okay, so notice that's a difference in those numbers there. It's not the third term, it's the second one. Okay, so that is what I'm gonna have to calculate here. Now I can pull out pretty easily from here that that's a sub 1 and that's my common ratio r. So I'm just gonna have to do basically 2 different problems. So for the first 9 terms, a sub 1 is 5 minus a sub 1 times r raised to the n, that's going to be the 9th term, over 1 minus r. Okay, throw that in my handy dandy calculator. 2 to the 9th times 5 minus that answer, and then I'm dividing that by -1, so that's 2,555. Okay, and now I'm going to subtract from that the sum of the first 2 terms in the sequence. So this is going to be my first term, still 5, subtracting first term times the ratio, still 2, but now this is just going to be a 2. And it's going to be over 1 minus 2. Okay, well, 2 to the second is 4, obviously, times 5. 5 minus 20 is -15, divided by -1, that's 15. So what we figured out is that when we look at this list, right, we just figured out that the total of the entire thing is this 2,555, and the sum of these first 2 numbers here is 15. So if I take this whole total of the whole thing and I subtract just these 2, that'll give me what's left over, which is what the problem asked me for. Okay, so when you actually subtract those, 2,540. So that is the sum of the third to the 9th term of this geometric series, okay? It's a little bit different. You gotta kind of make sure that you wrap your brain around the fact that you can't just plug this into the formula, and also that these guys aren't gonna match, okay? This guy right here, most commonly messed up thing on the test when we get to this, okay? So just be aware that that's the big mistake and make sure you watch out for those problems.